Okay, in this video, let us see how we define quantum Fourier transforms. Partially, we are all aware of Fourier transforms. Okay, now a quantum Fourier transforms, what it does is it helps a quantum computer. It helps a quantum computer to compute something analog to an quantum analog to the Fourier transforms. It helps a quantum computer to compute a quantum analog of the Fourier transforms. As we all know, after doing a course on quantum computing, it is not about deleting whatever is there about classical computing. It is about revising the classical computing with a faster pace and for more complex problems. Okay? Yeah. A quantum computer can use this quantum Fourier transforms as a quantum analog. That's the basic idea, guys. A quantum computer can be used to compute a quantum analog of the Fourier transforms. Okay, yeah. How do I start the definition of the quantum Fourier transforms? Obviously, with the quantum qubits. Okay, how do I consider qubits? Okay, that let's see about that. Consider two states of d is equal to n qubits. Okay, let that states be ket x and ket y, guys. Ket x is nothing but xn minus 1, xn minus 2, and so on till x naught. Okay, n qubits. So x naught to xn minus 1 would be n, right? Y n minus 1, y n minus 2, and so on y naught. Okay, where each xi, yi belongs to 0, comma 1. Okay. Then, see, I'm defining the dot product first. That is x dot y. Ket x dot ket y, of course. Okay. It is x naught y naught plus x1 y1 plus and so on xn minus 1 yn minus 1. Okay. Now, the quantum Fourier transform maps the states ket xi into the state. Okay. The quantum Fourier transform maps ket xi. What is ket xi? Let me write first. It is xn minus 1. I am redefining it. X naught into the state. How does the state look like? I'll write with a different color. 1 by 2 power n by 2 ket 0. Why it is 2 power n by 2? Let's justify. Okay, don't worry. Plus e power 2 pi I 0 dot xn minus 1 ket 1. Okay. Into tensor product of ket 0 plus e power 2 pi I 0 into xn minus 1. Of course, xn minus 2, xn minus 1. What this is I will define, guys. Don't worry. Okay, and it goes on and on, guys. It goes on and on. What's that? The square braces, the power of e power. What that denotes, I will define. Don't worry. Tensor product Okay. The last term would be something like e per 2 pi I 0 into xn x naught, of course, x1 and so on, xn minus 2. There is no comma, by the way. Xn minus 1 get 1. Okay. This is how it is defined for quantum Fourier transform. Now what this, the notation, let's see what the notation stands for. Notation, let me write. What the notation stands for is uh, the x naught by 2, whatever is there that has to come is represented by 0 into x naught, guys. The first term. Okay. Yeah. X naught by 2 squared plus x1 by 2, that I am representing by 0 into x naught into x1. Okay. Next, you see, you will understand the rhythm. X naught 2 cube plus x1 by 2 squared plus x2 by 2, 0 into x naught into x1 into x2 and so on. This is written to represent the binary fraction, guys. Binary fraction. Okay, we have the superposition states and the introduction of the phases also here in the quantum Fourier transforms. If you observe, of course, the superposition state, the ket 0 plus ket 1 is there, along with the introduction to phases. Okay, I will write here so that you will understand. What are there? Two things are there here. Two things. What are they? Superposition state as well as plus introduction to phases. Introduction to phases. Phase, you know, right? Phase matrix and all that. If you want, I can write. Of course, in the next example, anyways, I'll talk about that one. Okay. Now, for superposition state, guys, remember, always you remember, for superposition, I'll be needing Hadamard gate, guys. Superposition state, I'll be needing Hadamard gate. H gate. Okay. Now for the phase what I will be needing, it's obvious na? For the phase what I'll be needing is my phase shift gate. Okay. Phases, for the phases, I'll be needing what? Phase shift gate. Phase shift gate. I can write that for you. Hadamard gate anyways is obvious. Okay. Phase shift gate, something like the phase shift gate, discrete phase shift gate also I can call RK. Of course, different ways are there, guys. Is 0 e power 2 pi I by 2 power k, guys. 2 power k. This is how I will write. Of course, I can write the RK action on ket 0 and ket 1, guys. Of course, if you ask me Hadamard gate, guys, H of ket 0, H of ket 1, superposition state it gives na. H of ket 0 gets transformed to what? If I apply Hadamard gate, you ought to know about it. Okay. Do check that. Do check that. You will understand what I am talking. H of 0. If I apply H gate on 0, what happens? If I apply H gate on ket 1, what happens? Do check that. You will understand. I will write this because this is new. Phase shift. What happens here is once I apply to ket 0, of course, do verify. Ket 1, this is equal to what happens is e pi 2 pi I by 2 power k ket 1. Okay. Now, I have defined the quantum Fourier transform state. First, I have defined this ket xi, how it is mapping that I have defined. Okay. What are all the things that are involved in it? As the superposition state is there, the phase shift also has turned up along with the tensor product. There is also a shorthand notation like your x naught 0 into x naught 0 into x naught into x1 kind, which denotes the binary fraction x naught by 2, x naught by 2 square plus x1 by 2 kind of things. Okay, and it goes on and on. I just stopped with 3 terms only, guys. Okay, yeah. Now, let us see how the quantum Fourier transform operator works. With that, I think that knowledge is enough. No applications and all are there, right? So, quantum Fourier transform is implemented on Hadamard gate and controlled. This is all. I will write the another name also. Controlled discrete phase gate also. This is called controlled discrete phase gate. Another name for it. Okay. So I'll write here quantum Fourier transform. Highlight this. If you understand this, quantum Fourier transform is done. Quantum Fourier transform implementation. Implementation is done. Okay. Using Hadamard gate, H gate plus controlled discrete phase gate, guys. Phase gate. Okay, I'm not writing the whole thing because just to save time. Now, let's write the quantum Fourier operator. Okay. Quantum Fourier operator denoted by UF, guys. Denoted by. Of course, there's another your unitary operator. Okay. UF. This is capital F, by the way. I'm sorry. This is capital F. Quantum Fourier operator on ket x. How does it look like? Of course, ket x is an arbitrary state. How does it look like? Let's see. UF of ket x. Of course, again, this is capital F. When it is small f, it is unitary operator, guys. You know about it. 1 by under root 2 power n summation y is equal to 0 to 2 power n minus 1 e power 2 pi I x y by 2 power n ket y. Okay, this is how quantum Fourier transform is defined. Okay, of course, now once I say this, the previous notation was there, na quantum Fourier transform map was there, na that notation comes into picture in the power of E. Okay, I will rewrite this again so that you have a clarity and you need not refer any other books for it. By it is 2 power n, guys. Okay, now this notation from where I will get is from this. I'll be getting it from this. Okay, yeah, I will rewrite it. Here I'll try to rewrite it so that you get a clarity and then things are done. Okay, this is all about the quantum Fourier operator, guys, acting on an arbitrary state, capital X. Okay. This is equal to 1 by under root 2 power n summation y is equal to 0 to 2 power n minus 1. Okay, e power 2 pi I. xy I have written now. What that xy stands for is the previous notation. Just see here. Y naught 0 into x naught into x1 and so on xn minus 1. Okay. Plus y1 plus y1. Of course, this bracket should not be there because finally it closes. Y1 into 0 into x naught into x1 and so on xn minus 2 plus and so on. Okay, I am writing here only plus yn minus 1 0 into x naught. You know this notation. I have already rewritten. Close the braces, the power braces. Now what else I have is ket y is what I have. Okay, this is what is quantum Fourier transform, guys. Of course, once I start expanding it, writing on different things, using different properties, I will get all complicated things about quantum Fourier transforms. I think this much is enough regarding quantum Fourier transforms. Now, what is ket y if you ask? I will write that, and where ket y is nothing but my tensor product of ket y naught, ket y1 and so on ket yn minus 1. Okay, if I write the same thing, finally what I will get. This is optional, guys. The final version is optional. The above version is enough. Okay, what's the final version? U capital F of ket x. This is equal to 1 by under root 2 power n summation y is equal to 0 to 2 power n minus 1 e power 2 pi I y naught 0 into x naught and so on xn minus 1. Okay. Yeah. Ket y naught. Okay. Tensor product. Okay. And so on tensor product. E power 2 pi I y n minus 1 0 into x naught. Okay. Ket yn minus 1. This is what is the final version of the tensor product. Of course, there are again different modifications and all the things. This is all about quantum Fourier transforms, guys. Yeah. Now, let us see one more example. One more numerical. The next numerical is on, what's that? Yeah, single qubit gates. Second question, single qubit gates. What that is the action of single qubit gates. Okay, what is the action of single qubit gates on the computational basis kind? Okay, uh, what are single qubit gates? If you know, your job would be done. That's it. Action of any two single qubit logical gates. Okay, logical gates, single qubit logical gates are, of course, X, I can say. Okay, X is a single qubit gate. Okay. Of course, X, Y, Z all are single qubit gates. Just see here what's its action. Suppose if I have ket xi, guys. What is ket xi? The superposition state I'm considering. Alpha ket 0, beta ket 1. If I take, just see, ket xi in, I will say in, this is equal to alpha ket 0 plus beta ket 1. Okay. Now, if this is being sent to the X gate, what output comes? Let us see. Ket xi out. How it comes, guys? Just tell me. There is a bit flip, na? There is a bit flip. What happens? The 0 bit flips to, I'm sorry, 0 bit flips to 1 and 1 bit flips to 0. This is how I should write. Of course, you can explain using, of course, x gate is equal to x gate on 0, x gate on 1. You take the matrices 0, 1, 1, 0, apply it on 1, 0, get the output. Similarly, 0, 1, 1, 0, apply it on 0, 1, get the output. Check what happens. Okay. Yeah. Now, another single qubit gate I can take is Y or Z. Anything is fine. Y I can take. Of course, phase flip also. Phase flip gate also I can show. Just to see Y gate I can show you. What that is ket xi. Ket xi in I am sending, guys. Of course, you know what ket xi in is. Through the Y gate I am sending it. What happens through Y gate? Ket xi out. How it comes out is, of course, there is an I. There is an I. Okay. Yeah. There is a bit flip as well as phase flip. Bit flip, ket 0 becomes ket 1. Phase flip, what happens is plus becomes minus and ket beta, I mean ket 0, ket 1 becomes ket 0. Okay. Of course, I is multiplied to both. I can write I separately, of course. Okay. This is all about Y gate, guys. The single qubit gate. Z gate you see here. Z gate, you see what happened. There is only phase flip, guys. There is no bit flip. Okay. If I am sending in, then xi out would be something like this. What happens is Alpha ket 0 is as it is, no phase flip. There's a bit flip. That means what? Plus becomes minus. Okay. Now, I can also tell you, I can also just write the phase flip gate or the Hadamard gate also. These are all single qubit gates, guys. Okay. Hadamard gate, what happens? Quantum interference I talk about, right? Hadamard gate gives me the concept of quantum interference. Anyways, what happens? Let us see. Get out would be complete change, guys. Alpha plus beta by root 2 get 0 plus alpha minus beta by root 2 get 1 it becomes. Okay. Do check it. Of course, there's a shorthand notation for it, guys. Alpha get plus beta get minus. You can ask me, ma'am, what's this notation? If you say, again, I'll talk about atoms and electrons where there is a spin, positive spin, negative spin, because of which I'm using the symbol plus and minus. And again, I correlate it with the quantum mechanics. Okay. I'll just tell you about the phase shift. No. Yeah. The phase shift gate. Okay. If I am talking about phase shift gate, I can denote it by P, guys. Okay. What happens? Let us see. P. If I'm passing it through P, any ket xi, okay, random ket xi, if I'm passing it, ket xi in, what it becomes is, it was actually alpha 0 plus beta 1, na? Beta ket 1. Now, what it has become is alpha ket 0 plus e power I theta beta ket 1 it has become. Okay, this is how phase flip happens. Any of these gates, accordingly, you can discuss, you can give. By the way, these are all single qubit gates, guys. Why single qubit is because, see, if I say 2 qubits, guys, how they'll be, 4 by 4 matrix. If I say single qubit, it would be a 2 by 2 matrix. Okay, that's the simple way to remember, right? After this, yeah. Next thing that I would like to talk about is your quantum swap test. Quantum swap test. Quantum swap test. Okay. If you are asked to give the diagram or something like that for the quantum swap test, what do I do is, it's very simple actually, again applying the Hadamard gate and all. Just see the circuit diagram. Circuit diagram. Okay. What happens is, see, I'll be taking 3 qubits, okay? The ket 0 is stored in ancilla. Ancilla, that means the temp, okay? There is a ket A and ket B. By the way, quantum swap test is used to find the dot product between two states or vectors, okay? Yeah, see what happens, guys? Electrons so big. Okay, there is this Hadamard gate that I am applying, okay? Now it goes out. One more Hadamard gate I will apply. 2 times I will apply, guys. Okay. How the circuit look like, I will tell. If you, I can just give you the explanation as well. Okay. B. We denote like this. This is the circuit diagram for quantum swap test. Okay. Yeah, this I can say here there is a transmission. I mean intermediary transmission or whatever. Xi2. Okay, and this would be your ket Xi3. Okay, what this means, let me explain to you. Of course, this is the circuit to find the dot product between two vectors, guys. What exactly this means is, see, I'm sending 0, 0. I'm sending Ancilla bit. Of course, this I will call it to be register 1, ancilla register 1 and register 2. Okay, see here how they will look like is 0, A and B. They will look like this. Now, once after this, what I'm doing, I'm sending this through Hadamard gate. Okay, Hadamard gate 0 only I'm sending. Okay, so H if I apply here, guys, what happens? Very simple, looks so complicated, but H if I apply, H of 0, just now I have seen what it gives me is H of 0, what it gives me is ket 0 plus ket 1 by root 2 is what it gives me. A and B are as it is. Okay. Next. Next you see, I will separate them. 1 by root 2 I will put it out. I'll put out. What happens? Ket 0, ket A, ket B plus ket 1, ket A, ket B. Okay. Yeah. Now, controlled gate swaps the registers for 1 only and it doesn't distinguish anything for 0. Okay, or in other words, I can say Fredkin gate. Fredkin gate is there now, this controlled swap gate. I will just write here. Between this H and H, controlled, controlled swap gate. You know about it. Or the Fredkin gate. It's called Fredkin. We discussed about this. Fredkin gate, what it does is only if there is one, it flips. Okay. It doesn't talk about or it ignores. Fredkin gate swaps if the control is one, otherwise it doesn't do anything. I mean, it doesn't make any change. Okay. So what happens would be, if you look at, you will understand what I'm talking. Ket 0, ket A, ket B. Okay. Now what happens here? Where there is ket 1, there's a flip of the register. Okay, bit flip will be there, like there, a register flip will be there. Now next is what is happening after control gate. Again I'm applying H here, guys. Apply H again. Applying H on the output. Two H's are there. You can see in the this thing. Okay. No, why I'm telling you is to remember the circuit. Okay. Yeah. Now once I apply H again, what happens is it looks something like 1 by root 2 H ket 0 ket A ket B plus H ket 1 ket B ket A. Okay, yeah. See the output, how what happens to it. Ket 0, H ket 0, I know. Of course, 1 by root 2 vanishes off. 2 times 1 by root 2 will be there from H ket 1 and H ket 0. So it becomes 2 only, guys. Okay. Now H of ket 0, I know it is 0 plus 1 ket A ket B. Okay. Just enclose this plus. Here H of ket 1 is what? H of ket 1 is what? Ket 0 minus ket 1 ket B, ket A. Okay. Root has become, root 2 has become, 2 times root 2 has come. So it has become 2 only. Okay. Yeah. 1 by 2. What happens? You just see. Ket 0. I separate. Okay. Ket 0. Ket A, ket B. Once it happens to ket 1. What happens? There is a bit flip. Right. What happens to it? Yeah. Of course. Ket 0. Common things if I take. Ket B, ket A. Okay. Yeah. Ket 1 common things if I take. Ket 1 common things if I take. There'll be a minus. Okay. Just see here. Is it perfect? Is it okay? Yeah. Next, what you will do is, now this output, whatever I'm taking, the ketzai or whatever I'm calling it, in that See, whatever, this is the output, guys. This is the output. This is it. This is it how I will apply control gate. Now, there are cases. Case 1. Okay, what the case 1 is, if ket A is equal to ket B, what happens? See here, guys. See here. What happens to this and what happens to this? Second term manages off. Only first term will be there. If ket A is equal to ket 1. I mean, ket A is equal to ket B. What happens? 1 by 2 ket A, ket B plus ket A. I can call ket A, ket B. Okay? Huh. If ket A is equal to ket B, it is twice of it. Yeah. Now, also I can say the controlled qubit will be in the state ket 0 only. Okay. Only in ket 0. I have only ket 0. If ket A is equal to ket B. Okay. Yeah. Here. Controlled qubit will be in get 0 only. Of course, there are remaining things how to estimate and all, how to estimate it and all the things. What that is probability of get 0. If I start estimating, I know probability would be the coefficient whole squared, na? What's the coefficient of get 0? That whole squared I will take. What that is 1 by 2. Get A, get B. Of course, twice it is, na? It is twice. So what happens is, and write like this only, ket B whole square. Okay, so if I expand it, things would be sounding weird. What that is I'll have two different things. Squared in for complex numbers would be different, na? What that is one is the number and the other is its conjugate, right? Conjugate or dual would be something like A, B plus B, A, this is one term. Another term would be the one. Ket A, ket B plus ket B, ket A. Okay. The dual, that's it. Because it's in complex, right? Now if I multiply, what happens? Just see here. If I start multiplying, I'll have inner product of A into inner product of B plus inner product of AB, inner product of BA, right? This into this, okay, has given me this. This into this has given me this. Okay, now coming to the second term. What it gives me is ket B A and ket A B. Ket A B. Okay, plus ket B, I mean inner product of B and inner product of A is what I will get. Now, next, I know that the inner products of the same terms are ones and the inner products of the different terms are zeros because of the orthonormality. Okay. So what I'll have 1 plus, this one is 0 plus 0. Okay, of course, 0 probably I need not say. Just a second. I can write it as twice because the same term is there two times as of now. Okay, so what do I get would be, this is 2 and this is 2 into ket A, I mean inner product of AB, inner product of BA. Since both are equal, what happens is 1 by 4. Okay, of course, I can write this as 1 by 2 plus 1 by 2 and this term would be, since both are equal, I can write it as a whole square. Okay, this is the origin for your, what's that? quantum swap test formula. Okay, now I will just write here probability of ket 0 is what? 1 by 2 into 1 by 2 inner product of AB whole squared. Probability of ket 1, how will it look like? Is 1 by 2 minus 1 by 2 ket AB whole square. Of course, I suggest you to look into the circuit, guys. This is just a small explanation. When A is equal to B, this turns out to be 1 only, guys. Initially, I was telling, right? When A is equal to B, just a second. When A is equal to B, ket A is equal to ket B, what happens is P ket 0 turns out to be 1, P ket 1 turns out to be 0, as I was telling initially. Okay. When one is perpendicular to the other, when ket A is perpendicular to ket B, things will change in a different way. P of ket 0 would be half, P of ket 1 would be half. Okay, this is it about quantum swap test. I think this much is enough, guys. Okay, next thing is the Deutsch algorithm. Let's do the Deutsch algorithm part and then finish off. Yeah, the Deutsch algorithm. Let's do this. I think I'm clear regarding quantum swap test, guys. I think there should be no doubt about it. The Deutsch algorithm. Let me do the Deutsch algorithm. Yeah. The last numerical for this video, that is for fourth one, for f of x is equal to 1, apply Deutsch algorithm for the state ket 1 and 0. Ket 1, 0. Okay. Let's see how we will do it. Okay. Now, what are the steps of Deutsch algorithm? You need to remember. What are the steps? Let me just recollect. You apply again Hadamard gate, guys. First apply Hadamard gate, then the unitary operation, then again the Hadamard gate. What is the swap test if you ask me? First apply Hadamard gate on three things. One is the ancilla register I have. There are two random ket A and ket B, two registers, 1 and 2 are there. You apply usually one Hadamard gate can be applied only on one qubit, guys. If there are three Hadamard gates, I can apply on all the three simultaneously. So in quantum swap test, I have only one Hadamard gate and I know Hadamard gate's value when it is applied to ket 0 or ket 1. Okay. The ancilla register that I have taken it to be ket 0, guys. Hence, I have applied it on ket 0. Once I applied Hadamard gate, then I applied the Fredkin gate or the controlled swap gate, then again the Hadamard gate. Similarly, here Deutsch also. First the Hadamard gate, then the, see, it is a H, then the unitary operator. See, guys, there is a small change. The, what is that? Quantum Fourier transforms is U capital F, guys. Unitary operators use small f. Notation changes. Okay. Again, there are some similarities that is unnecessary now, right? First Hadamard gate, then the unitary operator, and then the H gate. That is it about the Deutsch algorithm. Let's see how we will do. For the unitary operator, I'll be needing the function. Here I have considered f of x is equal to 1, which is a constant function, guys. Constant function and its value is 1. Okay. Yeah. Now coming to the solution for it. How do I do it? I am being given the state ket 1 and 0. Okay, so I need two Hadamard gates. Okay, on ket 1 and ket 0. First 1 and then 0, guys. So, 1 on 1, 1 on 0. I'll be applying. Okay, I know the values, right? 1 by root 2 comes for both of them. So, I'll write it as 1 by 2. Huh? Right. Now, this would give me what? Ket 0 minus ket 1 is what I'll get here. Okay. Okay, I should not close this. Ket 0 minus ket 1 is what I will get. That is 1. Another one is ket 0 plus ket 1, guys. Multiply both of them. See what happens. 1 by 2, 0, 0, plus 0, 1, minus 1, 0. I think there is no doubt about it for anyone. Minus 1, 1. Okay, guys? Yes. Next, what I'll do? I'll apply unitary operator. Let's call this to be Ketzai or something, guys. Let it be Ketzai. Ketzai prime kind we will notate and go ahead. Okay. Now, what I'll apply? UF of Ketzai is what I will do. Okay. Yeah. So, what happens? Half UF of Ket 0, 0 minus UF of Ket 0, 1. No, plus 1. Minus UF of Ket 1, 0 minus UF of Ket 1, 1, guys. Okay? Now, how does this operator work? Unitary operator, how does it work? Just see here, I will write the outputs. Then we will know. Okay? UF of 0, 0. How does it work as 0, comma 0 XOR of F0, for which I will be needing the function value, guys. Okay. Now, what is F0? Whether it is F0 or F1, it is 1 only because it's a constant function. Okay. So, what happens? 0, 0 plus 1 becomes 1. 0 plus 1. Okay. Again, there's a shorthand notation, guys, that we'll be using, which is a 0, 1. Okay. I can write like this. Yeah. Now, UF of 0, 1 is there. Okay, so how do I apply it? Of course, I think it should be written like this. 0 and what's the unitary operator? Unitary operator is defined as a B. Just a second. Unitary operator is defined as a F of 0 into just checking 1 second. Yeah, XOR of 1 plus 1. Anything other than only 1, 1, XOR is 0. That is what? 0 plus 0 is 0. I mean, plus means what? XOR. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 or 1 plus 0 is 0 only. Only for 1, 1, 1 it is there. Okay. So what happens to this is 0, 0, guys. Okay. Now, UF of 1, 0. What happens to this is 1, comma 0 XOR of 1. Function value is 1 for anything. Okay. Now this is what? 1, 1. Okay. UF of what is remaining? 1, 1 is remaining. 1 is there. Now 1 plus again 1 is there. So it is nothing but 1, 0, guys. Okay. So finally I can write the output. I can write the output for UF. Once I write the output for UF, I need to apply the Hadamard gate. It looks a bit complicated, but then it's very simple, very simple. Okay. Yeah. What is it that I have done is UF of Ketzai is what I have done. What did I get? 1 by 2 is anyways there. For the first one, I have got it to be 0, 1. For the second one, I got it to be 0, 0. Third one has a negative sign, I think. Anyways, I will write negative first. 1, 1, and then negative only I'll write. I'll just check and then get back to you. Okay. Which has a negative sign? Both of them have a negative sign. Okay. So 1, 1 got transformed to 1, 0. 1, 0 got transformed to 1, 1. Okay. Of course, there are many changes, by the way. I'm just talking about the last two terms. Now, immediately next, what I will do is, this state, I will rewrite this. This is not looking good. Minus 1, 0. Okay. So this one, let us call it to be ket xi prime, guys, because instead of writing this whole big things, okay, now what I need to do is, yeah, ket xi prime is what? UF of Hadamard gate applied on ket 1 and ket 0. Okay, of course, this is again a shorthand notation for tensor product of ket 1 and ket 0, guys. Okay, now, uh, finally, I need to apply Hadamard gate for the first one. Na? For the first qubit, I will apply. For the second one, I don't apply. What that is Hadamard gate on, that's what is Deutsch algorithm. What the final step says is, apply Hadamard gate to the first qubit, leaving the second qubit alone. Okay. So what happens? 1 by 2. This term turns out to be h of ket 0. Ket 1 is as it is, guys. Minus h of ket 0. Again, ket 0 is as it is. Minus h of ket 1. No, this is plus. Minus h of ket 1 and ket 0. Okay. And then you know how to apply h of ket 0. What are the values of h of ket 0 and h of ket 1, right? Accordingly, you will write the answers. By applying, yeah, here I should write like this actually. There is one change. I mean, there's one probably the notation thing that I need to rectify. Just see. H tensor product of I. I'm not applying on it. That doesn't mean I should leave it. Okay. What I will do is I will write identity function. Now see what happens. I know what happens also. You can simplify it further, but I'll just give the hint and leave it off. What that is ket 0 plus ket 1 by root 2 again. Okay. 1 plus again the same thing. Ket 1 and ket 0 have same common thing, guys. And then ket 1 and ket 0 also have same common thing. What that is ket 0 minus ket 1 by root 2. Of course, ket 1 plus ket 0. Okay, is it fine? Of course, I can take out ket 1 and ket 0, guys. Okay. So 1 by 2, I can take out ket 1 plus ket 0 common. Okay. So finally, I'll be having what? Of course, root 2 also I think I can take common. So finally I'll have what? Ket 0 plus ket 1 minus ket 0 plus ket 1. Yes, sir. See here. This 2 get cancelled off. I'll get it twice. Okay. Of course, that 2 also gets cancelled off. So I'll be having ket 0 plus ket 1 plus ket 0 by root 2 into ket 1. Okay. So finally, my answer turned out to be something in. My answer has turned out to be something in ket 1, guys. Okay, the output, the first qubit is allowing us to distinguish, and hence the final output state. The final output state, I can just call it to be ket xi out. What that turns out to be is ket 0 plus ket 1 by root 2. Of course, I can call, you know what to call it anyways. This is what I'm getting. Okay. This is how I'll apply Deutsch. Very, very, very simple. Okay. With this, I'll end this video.